Okay, let's get started. Today we're going to talk about, so there's two more things that we want to do. There's only two more classes. Today we're going to talk about polar coordinates, which is a kind of different coordinate system. And the next time we're going to talk about complex numbers. And these are all kind of basic things that, fundamental knowledge that will be handy to you if you go on in calculus and take calculus or take higher math. Okay. So how many of you have seen polar coordinates before? Anybody seen polar coordinates? No? Okay, great. Okay. So, great. So polar coordinates. Okay. So you are all familiar with so-called Cartesian coordinates, right? For the plane. Right, so you've got a planar surface, right? You've got this two-dimensional infinite surface, and you want to associate, you want to give a way of specifying what point you're talking about on the plane, right? And so it's Descartes who came up with this idea, apparently while lying in bed, watching a fly move around his room. He said, "Oh, look, you can, here are the walls of my room, and you can specify the position of the fly by saying how far it is from this wall, right, which is this distance, and how far it is from this wall, which is this distance, right? So you can specify how far it is from that wall and how far it is from that wall, right? X and Y, and that gives you these two coordinates, and that allows you to put numbers on things in the plane, and opens the way to talking about like equations that describe shapes, right? So like the circle we can describe with equations and stuff like that, which was impossible before. So it opens the way to so-called analytic geometry. Okay, so that is the Cartesian coordinate system that you are familiar with. But there's another one called polar coordinates. And what that is a little bit funny. You instead of having these two lines meet at an origin, you instead just fix. So you have this point here on the plane, and you want to give it some coordinates. What you do is you fix some point, and you say that's going to be my origin. Okay, that's called the pole. I think that's why this is called polar coordinates. Okay, and then you choose a ray emanating from that point. Okay, you make a ray emanating from that point, and the way you describe this point is you say you look at the following. You make a circle go like this, and you count this ray as the zero angle. Okay, you count this ray as the zero angle. And then going counterclockwise, you measure the angle from there. Okay, so you say, okay, I'm gonna specify this point by looking at what angle it is and how far away it is, right? How far away it is. Right. So you get this number r, which is the radius of the circle, which is how far the thing is away from the pole, and you get this angle theta, which is the angle from this initial zero ray. Okay, so then you call this point r theta. In the book they write it like this, but I'm always, if it's polar coordinates, I'm always going to write it with brackets. Okay, I'm always going to write it with brackets, because otherwise, if I see something like 5 pi like this, I don't know what that means. Is that Cartesian coordinates, 5 comma pi, or is that polar coordinates, distance 5 and angle pi? So I'm always my habit is to use brackets here to say that this r theta is describing the point using polar coordinates. Okay, I think that should be done. That's better. Okay, so this is like, these are two equally valid ways of describing the plane, and neither of them is sort of more natural than the other, right? If an alien came from outer space and said, "Oh wow, you guys are using this. Don't you have any? This is kind of arbitrary. why did you, why are you using a 90-degree angle or whatever, right? There's more than one way to put a coordinate system on the plane. Okay. Okay. One thing you might wonder is what happens when you go into 3 dimensions, right? What happens when you go into 3 dimensions? Well, there are different ways to do it. There's so-called cylindrical coordinates. So this is just an aside, but you could do what's called cylindrical coordinates, where for the plane you use polar coordinates. Use polar coordinates down here. But then for the z-axis, you just throw on the Cartesian coordinate. So you'd have things like r theta z. And then there's something else called spherical coordinates, where it's more like a real extension of polar coordinates. Anyway, don't have to worry about that for right now. Okay. So polar coordinates. So let me put up some examples. Yeah, okay. Some examples. So let me just draw the Cartesian plane, just so we're kind of oriented. If I say like 1 comma pi over 2, then what does that mean? That means that we're distance 1 away from the origin, and we're at angle pi over 2, right? Distance 1 away from the origin, we're at angle pi over 2, so that let's say that's here, right? So that in Cartesian coordinates is the point 0, 1. Right? Everybody getting it? Right. That's 0, 1. If I say say like 1, 0, well, that's again distance 1 from the origin, but at the 0 angle, right? So you go from the 0 angle and you go you travel 1 length away from the origin, right? So that's here. That's this point here, which is still 1, 0 in Cartesian coordinates. Right. If I say like the square root of 2 comma pi over 4, where is that? Take a minute, take a few seconds and see if you can draw where that would be. Okay, turn to somebody nearby and say, this is where it is. Okay, somebody want to tell me where it is? Root 2 comma pi over 4. Anybody got an idea? Root 2 pi over 4. Or you can just describe it to me. Where is it? What is this? What does this tell us about the point? If I see root 2 comma pi over 4, what does that tell me? Nobody wants to say. It's okay. So it tells me that I'm distance root 2 from the origin, right? And I'm at an angle pi over 4, right? So I'm on the pi over 4, I'm at this angle, and I'm distance root 2. That, if you think about it, that's actually at this point here, right? Because this would be, this is 1, and right, for the Pythagorean theorem to work, this squared equals this squared plus this squared, right? So if you square, right, if I have a triangle 1, 1, then the Pythagorean theorem tells me that this length is the square root of 2, right? So that point is actually 1, 1. Anyway, don't worry about the square root of 2, but I hope you get the idea of this coordinate system. Okay, what if I had something like this? Square root of 2 comma pi over 4 plus 2 pi. Where would that be? Anyone see where that would be?
would be in the same place.
It'd be in the same place, right? Because you go out here, pi over 4, and then you add 2 pi to it, and you come back to the same place, right? 2 pi is just a full circle, right? So this is still the same point, 1 comma 1, right? Or if I have something like, say, -1 comma pi, where would that be? Well, I'd be in the pi direction, right, which is this way, but I'd be traveling -1 units away. So I'd go backwards, right? So I'd be pointing in this direction, but going backwards, and I would come to this point, right? So this is still going to be 1 comma 0, right? Right, because I've got angle pi, but I'm traveling -1 units of length. Okay. Anybody confused? Amy, you look a little confused. Are you confused?
Can you explain why the square root of 2 and pi over 4 is equal to 1 comma 1?
Yeah, sure. So, okay. So, think you're going to be on this line, right? This is the pi over 4, the angle pi over 4, right? Right. And you're going to be square root of 2 distance from the origin, right? Right? Square root of 2 distance from the origin. So what are the x and y coordinates? What are the x and y coordinates? Well, you know that that x and y have to be equal to each other, right? X and y have to be equal to each other because we're on this line, right? And you know that so this is x and this is x, and you know that x squared plus x squared equals 2, right? By the Pythagorean theorem, right? Because this is a right triangle, right? So that tells you that 2x squared is equal to 2. In other words, x squared is equal to 1, right? And so each of these guys is 1. Okay. Okay. We'll see something better. We'll see an easier way of seeing it in a second. Okay. But yeah, I'm just going to leave it this way for now. Okay. Anyone confused about anything? Yeah, Manuel.
The last one is -1 pi.
Yeah, sure. So let me redo that one. So here, right? So this is our 0 angle, right? So if we have an angle of pi, that means that we're going in this direction, right? So we're going in this direction, but we're going -1 units, right? So we're actually going to go backwards. We're going to go backwards to here, right? We're headed in this direction, right? This is our pi direction, but we're traveling 1 unit backwards, right? So that's going to be 1 unit in this direction, which is 1 comma 0. Okay. Does it make sense? Okay. 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 Anybody else? Okay. So these two things down here were just to show you that there's one thing that's a little bit funny about this system, which is that that there can be multiple ways of writing the same point, right? I could have written 4 pi here, right, and that would be the same thing, or 6 pi, or -2 pi, or 2k pi, where k is any integer, right? And that's always going to give me the same point, right? So there's infinitely many ways to represent every point. Okay, so that's something that's a little peculiar about the polar system. Just one remark. The origin, by convention, we say that 0 comma theta is the origin for any theta. Okay, because it just means that you can take any angle, but travel zero units, and that will just leave you right at the origin, right? So 0 comma pi is the origin, 0 comma pi over 4 is the origin, whatever. 0 anything is the origin, stands for the origin. Okay. Okay, let me come back to here and maybe in your notes, redraw this picture. Okay, redraw this picture. Maybe I should erase it and then redraw it, but I don't feel like doing it. Okay. So I'm gonna draw another picture of this, and we're gonna talk about converting between coordinate systems. Actually, I'm just gonna erase it and then redraw it. Okay. So suppose we have a point, and we know here's our point. Okay, this is our angle theta, and this is our length, our radius r. Okay, and we want to know what this point is in the coordinate in the Cartesian coordinate system, right? What is it in the Cartesian coordinate system? So in the polar coordinate system, it's r comma theta, right? We would like to know its Cartesian coordinates, right? Right. In other words, we would like to know x and y, right? The x, we would like to know this, and we would also like to know this. Okay. So what do you see about this, right? Well, this x and y are the coordinates of, right? X and y are the coordinates on this circle, right? So does anybody see a relation between x, y, r, and theta? Like if I have, suppose we're on the unit circle. Okay. Suppose r is 1. Suppose r is 1, and I have this point x, y, and I have this angle theta. What's the relation between x, y, and theta? This is the unit circle. Yes, Dawn?
Would it be cosine sine?
Cosine sine, right? X is going to be cosine theta, and y is going to be sine theta, right? And if we're on a circle of radius r, then that just changes to r cosine theta, r sine theta. Okay, things just get scaled. So this point here, x is actually going to be r cosine theta, and y is going to be r sine theta. Sometimes maybe it's easier to think of this in terms of triangles. If we're in the first quadrant, and this length is r, right? This length is, in that case, this is x and this is y, right? And you see that cosine of theta is x over r, sine of theta is y over r. Right, is the opposite over the hypotenuse. Cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. And so x is r cosine theta, y is r sine theta. Okay, so in terms of triangles. And that actually works in every quadrant. Okay. So it's actually easy to go from from polar to Cartesian. Okay, so for example, this one that was a little bit confusing, root 2 pi over 4, right? Root 2 pi over 4, so distance root 2, angle pi over 4. Angle pi over 4, right? If we want to change that, that's going to be r cosine pi over 4, comma, r sine pi over 4. Right? But what's the cosine of pi over 4? root 2 over 2, right? So we get root 2 times root 2 over 2. And similarly for the sine, right, we get root 2 times root 2 over 2, right? But that gives us a 2 over 2, which is 1, 2 over 2 is 1. Right? So we get 1 comma 1, right? Which is what we got over here. Okay, so going from the polar coordinates to the Cartesian coordinates, you just use cosine and sine. Okay, so you get r cosine theta. Right? So this point is actually going to be r cosine theta, r sine theta. What about let me have you do one. If I have 5 comma 3 pi over 4, what's that in Cartesian coordinates? Okay, turn to a neighbor and talk with them or work with them, whichever.
The distance is 5. So, yeah.
Isa, what, can you talk with maybe Vivi and Amy? Yes, if you don't mind.
Yeah. What's the cosine and sine?
Okay, anybody want to tell me how to do it? Anybody get it? Let's see. 7, 9. Vivi, it's you.
Okay. So,
Yeah.
with the 5 and the 3 pi over 4,
Mhm.
I wrote the coordinates as 5 cosine 3 pi over 4.
Yep.
And 5 sine 3 pi over 4.
Exactly, right. It's pretty, nothing to be worried about. It's just going to be r cosine theta, r sine theta, right? And so the only thing is, what are the cosine and sine of 3 pi over 4, right? So 3 pi over 4, right? This is pi over 4, this is 3 pi over 4, right? Right. So what's the cosine of 3 pi over 4? Do you remember?
I didn't get that far.
Okay. So remember that this guy here is root 2 over 2, root 2 over 2. Right? This guy here is root 2 over 2, root 2 over 2. This guy is going to be just a reflection of that. So it's going to be negative root 2 over 2, comma root 2 over 2. Right? So this is going to be, this turns out to be 5, or negative 5, root 2 over 2, comma 5, root 2 over 2. Is there a question?
No, we were just talking about how root 2 over 2 is the same as 1 over root 2.
Yes.
Yeah.
Yes. Yeah. So 1 over root 2 some people don't like to have, I'm not sure why this is, but in some K through 12 education, they say, do not put radicals on the bottom. It's okay, actually. Don't worry, nothing's gonna happen. I'm not sure why that happens, but well, I'm not sure where this taboo came from, but it's a false taboo. There's nothing in mathematics that says that you should not have radicals on the bottom. Nothing. Okay. So you can simplify it by multiplying by 1, by another cleverly chosen 1. Right? So you multiply that thing by 1, and you see that that is just root 2 over 2. Right? So this 1 over root 2 is the same thing as root 2 over 2. Okay. Okay. So now going backwards from Cartesian to polar. Cartesian to polar. So if you have something on the xy plane, and you'd like to know, you want to know its distance from the origin. Well, what's its distance from the origin? What's r in this case? If this is x and this is y, what's r? You know this. Stella.
X.
Well, x is actually this distance, so it's actually a little bit farther than x, right? Right, so you want to know the distance of this point from the origin, right? So not x, but anybody think about it for 1 minute? Okay, talk with a neighbor, say, I think it's this. Okay, anybody get it? Anybody see it? Aaron?
X squared plus y squared.
X squared plus y
Or like
squared.
it's like the Pythagorean theorem.
Use the Pythagorean theorem, exactly. So you use the Pythagorean theorem, you say, well, this is x and this is y, right? So r, right, this is the point x comma y. And we're basically asking, how far are you from the origin, right? And so that's gonna be x squared plus y squared square rooted, right? Square rooted. X squared plus y squared square rooted. So that's our r, right? So if we have a point here, 2 comma 1, say, then its distance is going to be the square root of 5, right? So it's r, right? That point, right? So x comma y turns into square root of x squared plus y squared, and then some angle, right? And so you need some angle. You need some angle here. The way you get the angle is by noticing that, well, the tangent of this angle is going to be y over x, right? The tangent of the angle is y over x, and so this angle is the arctangent of y over x. I'm sorry, the inverse tangent of y over x. Okay, right? So you see from this picture, you see that the tangent of the angle is y over x. So what's the angle? It's going to be the inverse tangent of y over x. Okay, so whatever that is. And I would be remiss if I didn't tell you that this is also called the arctangent. Okay, so when we say inverse tangent, when we say arctangent, arcsine, that just means the inverse function. So arctan. Okay, so so in this case, this point here, 2 comma 1, turns into, in polar coordinates, the square root of 5 comma arctan 1 over 2. Okay. Okay, so all we've done so far is sort of like introduce this new coordinate system, right? We've got the polar coordinate system, and like show you what it means, and then show you how to take the polar coordinates and convert them into Cartesian, and from Cartesian back into polar. Okay. Okay. Now we're going to go a little bit. We're going to talk about like equations and things in the polar coordinates, like what is a circle? How do you describe a circle? How do you describe distance and this sort of thing? So like the things that you do in Cartesian coordinates, we want to do in polar coordinates. Okay. So the first one is a distance formula. Right. Suppose you have 2 points. What's the distance between 2 points in polar coordinates, r1, theta 1, and r2, theta 2? Right? We do have a distance formula for x1, y1, x2, y2. Right? The distance between these 2 points is going to be the square root of x1 minus x2 squared plus y1 minus y2 squared. Right? You remember that? It's just the Pythagorean theorem. So don't copy that. We've seen that before. Okay. So you could, it would be kind of awful, but you could take these guys, change them into their Cartesian coordinates, and then use the Cartesian distance formula. That would be one valid, and that'd be fine. But there's kind of a cuter way to do it, which is you look at this, so you think, okay, what does this mean? Here's my pole, and here's my zero ray here, and I've got 2 points. Let's say that the first one is here, r1, theta 1, right? And then the second point is say here, r2, theta 2. Okay. And what we're looking for is this distance here. Right? We're looking for this distance here. Okay. Now, let me sort of redraw the problem. We know one length, we know another length, we know an angle, and we're looking for this thing here. Right? That's the problem, right? We know one side length of the triangle, we know 2 side lengths of a triangle, and we know the angle between. Right? And we're looking for the length of the third leg. Well, does this sound kind of familiar? Right? What are we going to use? The law of cosines. Right? Law of cosines. Great. Right? So the law of cosines, what does it say? It says that distance, which I'm going to call d squared is equal to a squared plus b squared minus 2ab cosine of c, cosine of the angle here, which is theta 2 minus theta 1. Okay, so that's our distance formula. D is the square root of that. I'll give you a bonus point on the fun for that. Okay, distance formula. Okay, so that's nice, right? And so if we want to describe a circle, we can actually get a formula, polar coordinates formula for circles. And now this is kind of awful looking, but I'll give it to you anyway. So you have this point here. So let's call this point R naught, theta naught. Okay. And you want the circle of radius r around it. Okay. Right? You want the circle of radius r around it. So what does that tell you? I'm sorry, you want the circle of radius d around it. Excuse me. Okay. So what does that tell you? That tells you that, right, that for the arbitrary, if we have, let this denote some arbitrary point on the circle, arbitrary point on the circle, right? So we want to describe that, right? And so what it have to be is that, right? You need that d squared is equal to r squared plus r naught squared minus 2r1, 2 r naught r cosine theta naught minus theta. Right? So that's your formula. That's your formula for the circle. So here's the formula for the circle. Centered at r naught theta naught and with radius d. Okay, so nothing impressive, I guess. Right. So let me give you a concrete example. So if the radius is 3, let's say that the radius is 3, and that the center is 1, pi over 2. Right. So you have pi over 2, you're 1 here, and you're looking for a circle of radius 3 around that center. Okay. So then you would just plug things in, right? You just say, okay, what does it say? It says 9 has to be r squared plus 1 minus 2r cosine pi over 2 minus theta. Right? Okay, so all I did was just plug in here, and you get this equation. And you can clean it up a little bit, maybe, by moving the 1 to the other side. You say like 8 equals r squared minus 2r cosine pi over 2 minus theta. It doesn't matter. It's the same thing. Okay. But so you're starting to get some sense of what a circle looks like in polar coordinates, right? Right. Maybe you can start to recognize, you see something and think, okay, that's probably a circle. Other examples of equations. Of polar equations. Okay, so here's one for you to think about. What does r equals 5? The equation, right? the equation r equals 5 look like? Right? What does the solution set look like? If they say r equals 5, what kind of points represent that on the polar plane? What does this represent? Well, what kind of points have r equals 5? Stella?
Would it maybe be like a circle with radius 5?
Circle of radius 5, center at the origin, right? Because this r means your distance from the origin, right? So all this is saying is that distance from the origin is 5, right? So this is a circle centered at the origin of radius 5, right? Which is nice because that's a lot simpler than saying x squared plus y squared equals the square root of 5, right? So for some things, describing them are easy. Is easier using polar, and for some things it's easier using Cartesian coordinates. Okay. Right. So this is right from the polar point of view. This is just all points of distance 5 from the origin. You could convert. So converting to Cartesian coordinates, what you could do is say, okay, r, remember, is the square root of x squared plus y squared. Right? So this says the square root of x squared plus y squared equals 5. Right? Well, I shouldn't have said square root of 5 earlier, just 5. Sorry. So x squared plus y squared equals 25. Right? The distance is 5. This is right, and then you'd see this and you'd say, oh, this is the circle centered at the origin of radius 5. Another example, r squared equals r cosine theta plus 2r sine theta. Okay, which you can simplify. I'm going to divide by r. It's r equals cosine theta. Nope, actually I'm going to leave it that way. Sorry. Let me just think. Okay, so this is one where it's a little bit tricky to look at it and say, it's not like this one where you just say, oh, look, this tells us this, right? This says that the square of the distance to the origin equals this thing plus that thing, plus twice that thing, right? So in this case, it turns out to be easier to convert. So let's convert to Cartesian, right? What's r squared? What's r? Can anybody? I know I'm asking you to just assimilate information instantly, which I could not do myself. But does anybody know what r squared is going to be? R, remember, was the square root of x squared plus y squared. So this is going to be the square of that, right? So remember, r was the square root of x squared plus y squared, and then so this is just going to be x squared plus y squared. Right. And then if we want to convert this stuff to the Cartesian coordinates, well, does anybody remember what we said a couple minutes ago? R cosine theta turns into what in the Cartesian world? X, yeah. And then r sine theta turned into y, right? So this is x plus 2y. Okay. So then you get this equation, right? X squared minus x plus y squared minus 2y equals 0. Okay. Which actually you can turn into, if you use completing the square on it, it turns into x squared minus 1/2. I'm not going to do it, but if you use completing the square on it, it turns into this, which is recognizable as a circle. Right? So it's a circle centered at 1/2, 1, and then the radius is the square root of 5/2. this is centered at 1/2, 1, and the radius is the square root of 5. Okay, so some of the problems that you're going to have in your homework are this sort of game. You're given something like this, and then you switch it over to Cartesian coordinates, or vice versa. You're given something in Cartesian coordinates, and they ask you to switch it over into polar coordinates. So, for example, these will mainly be sort of conversion exercises. So they'll give you something like this: 3x minus 4y equals 2. And they'll say, what does that look like in polar coordinates? And you'll just say, well, x is r cosine theta and y is r sine theta. And then you just write it in polar coordinates. 3r cosine theta minus 4r sine theta equals 2. Okay, so going from Cartesian to polar is the easy one. The more tricky one is going from the polar back to the Cartesian. Everybody see how this was done? Right? You just substitute. Right? We know that x is r cosine theta. We know that y is r sine theta. Right? Here, remember, this is arctan y over x. So basically, it's just using these conversions to switch one equation to another. Okay. Let me just do one last example. Sorry to keep you a little bit over. So here's one, number 27. R equals 2 cosine 2 theta. 2 cosine 2 theta. So it's any point where the radius, the distance to the origin is twice the cosine of twice the angle. Okay. Yeah. So in this case, what you want to do, so you would like to use x equals cosine theta, y equals sine theta, right? You'd like to use that, but instead you've got cosine of 2 theta, right? You've got cosine of 2 theta, and so the trick is to use a trigonometric formula that we got before. So, so you recall that cosine 2 theta is actually cosine squared theta minus sine squared theta. Oh, I'm sorry. X is r cosine theta and y is r sine theta. Sorry. Right. Okay. So, right. So we can rewrite this as r equals 2 of that. Right. That's cosine squared theta minus sine squared theta. Right? We want to convert everything into x and y, so we want r cosine theta and r sine theta. So what we do is we just slide them in. We say, okay, we need r squared here. Well, just multiply by 1. We multiply by r squared over r squared. Multiply this guy by r squared over r squared. Okay, and now we've got the r squared, r cosine theta on the top. We've got the r sine theta on the top here, and now we can do the conversion. So we say, okay, r is what this equation turns out to be is x square root of x squared plus y squared equals 2x squared over x squared plus y squared minus minus y squared over x squared plus y squared. and that would be the end of it. I think I went a little too fast through that, but let me just, I'm sorry to really keep you over, but let me just say it again. Right, you have this thing, and you'd like to convert it into Cartesian coordinates. So what you do is you use the trigonometric identity that we got before. That changes our cosine 2 thetas into cosine thetas and sine thetas, right? Which is good because we want cosine thetas and sine thetas, right? So we change this thing into cosine squared theta minus sine squared theta, right? And then we slide in the r's by just multiplying by 1. So we get r squared cosine squared theta on the top, right? Which turns into x squared, right? Right? X squared is going to be x squared is r squared cosine squared theta. Y squared is r squared sine squared theta, right? So we get x squared over r squared minus y squared over r squared, right? And that gives us the equation in Cartesian form. Okay, sorry to keep you late.